Hello, today we're going to be talking about structure 1.5.1 and 1.5.2, which is all about the ideal gas model. So the ideal gas model is a model for the behavior of gases that has a certain number of assumptions that it makes. So like if it were to behave perfectly, it's this ideal gas model. So the first assumption that you need to know is that their gas particles are always in constant, rapid, random motion. So the particles are always moving freely and randomly. Our second assumption is that the particles of a gas have a negligible volume. Can't write negligible. There we go, volume, negligible volume. So that word negligible, the particles themselves are so small in comparison to the size of their container that they effectively take up no space. Our third assumption is that the particles exhibit no intermolecular forces. No intermolecular forces. I'm going to use IMFs to abbreviate that from now on. Intermolecular forces. So they don't stick onto each other. And that leads us to number 4, which is that any collisions of an ideal gas, so either with each other or with the walls of the container, the collisions are perfectly elastic. Perfectly elastic. And so that means that all kinetic energy is conserved. There's no loss of kinetic energy to other sources. So those are your 4 assumptions. And are any real gases like this? No. But you can get pretty close to ideal gas behavior under certain conditions. And so it becomes a useful model for gas behavior under certain conditions. So let's talk about pressure, gas pressure. Pressure occurs because gases are constantly colliding with each other and with the walls of their container. We can measure the pressure of a gas by the collisions that it's making with the container. And pressure varies with volume, temperature, and number of moles. So if I were to have, so let's talk about volume, pressure versus volume. As pressure increases, volume decreases, and vice versa. Pressure decreases, volume increases. So when I'm looking at pressure and volume, I want to think about the same number of particles. If they are packed together in a smaller volume, they're going to collide more frequently with the walls of the container because there's less space. A larger volume is going to have less pressure because it's going to collide less frequently with the walls of the container. Now, if we're talking about pressure and temperature, as the temperature increases, then the pressure increases, and vice versa. So same volume this time, same number of particles still. But at higher temperatures, they're moving faster. They have more kinetic energy. So they're moving faster, they're going to collide with the walls of the container more frequently and with more force. If they're moving slower, then they're going to collide less frequently and with less force. And then when we're talking about the number of moles, as you have more moles, you're going to have more pressure. So if we keep volume and temperature the same, more moles versus less moles, the more moles there are, the more there's going to be collisions, and the more pressure there's going to be. We're going to be looking at these relationships more quantitatively later, but I wanted to show them to you now because we're talking about the ideal gas law. So these are the relationships you should really understand for gases. Now we mentioned real gases. Real gases do not perfectly follow the ideal gas law. Real particles have a volume that is not negligible. So if you have an ideal gas, consider like the space that those little dots take up is so small compared to the size of the container. A real gas, you're going to be thinking about these particles are taking up space. And so that reduces the available space to move around it. The other assumption is that particles do not have any intermolecular forces, but real ones do have intermolecular forces. So when they're moving around their container, if they are to attract each other, that's going to interfere with their collisions. If they're pulling each other together, sticking to each other, even if it's fleeting, like if it's London dispersion forces, then it's not going to completely follow the ideal gas law. And so that's going to affect your pressure. It's going to affect the strength of your collisions and the frequency of your collisions. Okay, so that leads us to this example, explaining the reason for the difference in behavior between real and ideal gases at low temperature. So let's say we've got our two gases here. If one of them is going really fast, high temperatures, they're going to collide, and they're not going to be able to form attractions as well because they're moving so fast. They're not going to want to stick together very much. But at lower temperatures, if they're moving slower past each other, they're more likely to form those intermolecular forces that hold them together. And intermolecular forces are going to slow the collisions even further. They're going to decrease the frequency of collisions and make it behave less ideally. And so then under what conditions of temperature and pressure are real gases likely to behave the most like ideal gases? That's at high temperatures. They're moving fast. They can't form those intermolecular forces. And then at lower pressures, for the same reason, they're less likely to collide and form those intermolecular forces. Also, low pressures are going to help mediate the effect of the particle's volume. If it's at a really low pressure, they're going to be typically more spread out, and that the volume difference isn't going to matter as much. I also want to go ahead and point out that very small molecules and very non-polar molecules are going to behave typically more ideally. And that's because they're going to form weaker intermolecular forces just normally. So small molecules can form weaker London dispersion forces because they have smaller electron clouds. And then nonpolar molecules are not going to form those dipole-dipole interactions or hydrogen bonding, for example. So if they only have London dispersion and they have weak London dispersion because they're very small, they're going to behave more like an ideal gas. And that leads us to this linking question. Under comparable conditions, so if we're looking at same temperature, same pressure, why do some gases deviate more from ideal behavior than others? And that has to do with their size. So the electron cloud size is going to affect their intermolecular forces, and it's also going to affect the volume of their particles. Because remember, an ideal gas has a negligible volume of the particles. So if they're big molecules, they're going to take up more space, and so that is less ideal. But if you have a larger electron cloud, then you're going to have stronger dispersion forces. I'll abbreviate LDF, London dispersion forces. And so that's going to make them deviate more. Another example would be polarity. The more polar the molecule, the more likely it's going to form stronger intermolecular forces to deviate more from ideal behavior.